Okay, so we talked about reactions and how we express the conditions, and we want to look at next how does a reaction occur. Let's say we have such a state machine. We have an input signal X, which takes values present, absent, so it's a pure signal. The output is Y, also takes two possible values, as itself is also a pure signal. And we have two states, S1 and S2. S1 is the initial state, and we have a transition from S1 to S2, and we have a label X/Y. So what we're saying here is we want to use the label on the arrow to define what will be the condition for this transition, and what will be the actions taken while we do the transition. In this case, all the inputs are discrete, and a reaction occurs when any input is present. So regardless how you or what you put as predicates as the guard, so this this part before the / symbol, if any of these input signals is present, this reaction will occur. Reaction will cause these predicates to be evaluated. So if X is present, we'll evaluate this condition, and because we say X, that is to say, if X is present, this transition is enabled. So we'll take this transition from state S1 to S2. And because of that, we also output Y as present. Okay? This is called event-triggered model. So what we're saying here is X is present, which means that there's an event on this input signal X. So it's present, and as a result, this transition will take place. And consequently, the output action will be taken, and that means we're going to output present on the signal Y. Okay. Again, this is the event-triggered model. Now, let's look at a very similar state machine, almost the same, except that in this case, on this arrow, the label is not X /Y. The question here, well, let's suppose X, Y, again, discrete and pure signals. When does this transition occur?
When X is absent.
Okay. Any other comments?
The current state is S1.
Yes, the current state is S1. So let's look at this interesting example. What are the input signals? X, right? We only have one input signal. We will, if you look at this predicate, the not X, from our earlier slides, we know that this is to say, if X is absent, this condition is going to be true, right? So ideally, we expect that this transition will be taken. But here's the issue. The issue is the system, the reaction only occurs when any of the input signal is present. Let me say that again. So the reaction occurs when any of the input signal is present. That is to say, if X is absent, we basically will not evaluate this. And because we only have one input signal, and if this input signal is absent, we will not have this reaction. As a result, this guard, this predicate part, will not be evaluated at all. So this transition will not happen. So I think this is a little bit tricky to understand if you just look at this finite state machine. Because the way we design this state machine, we use the event-triggered model. And in particular, in this example, we are saying that we're gonna be, the condition will be X is absent. In this case, because the input signal is absent, this reaction will not be triggered, will not occur. So it will not evaluate the predicate. As a result, it will be, not taking this transition. If you think about a more concrete example, if you don't have changes on the input signal, if you don't have changes, if there's no car driving, and then your system state will not change because your input signal is absent, right? Okay, so we look at, in the previous two slides, two very similar finite state machines. Their inputs are the same. There's only one input signal X, and there's only one output signal Y, and both X and Y are pure signals, which means that they take value either present or absent. The transition diagram is a little bit different. The predicate, the condition is, this case is X is present, and in this case is X is absent. Now, one thing we assume differently here is that suppose all the inputs are discrete and a reaction occurs on the tick of an external clock. So although it's not drawn here, but we assume there's an external clock which will give you this ticks at certain interval based on the period of the clock. And in such a case, we say this is a time-triggered model because the reaction will occur every clock tick. So no matter what you have as the input signal, present or absent, this condition, this guard will be evaluated on every clock tick. Could be the rising edge, could be the falling edge, but we're gonna be evaluating this predicate as the guard to decide whether this transition is taken or not, or in this case, whether this transition is taken or not. So it may happen.
Professor?
Yes.
Are time-triggered models more practical in general or just in this instance? Are there cases when event-triggered models are more practical or not really?
Well, I would say, let me give you one example. If a event is very rare, right, very rare, it makes sense to use an event-triggered model because you may have to wasting a lot of energy if you check that condition every clock cycle.
Oh, that makes a lot of sense. Thank you.
Yeah. That was a very good question. But what we want to emphasize in this example here is that, for time triggered model, it will not, have that case where your predicate was not evaluated. This will be evaluated every cycle. And of course, we're going to be looking at the status or the value on the pure signal is present or absent. And based on that, we'll take the transition or not taking the transition.
Professor, for an example of time trigger model, what would the traffic light be one of the example?
Can you repeat that part?
For time trigger model example, would the traffic light example be one of the example for a time trigger model?
Okay, yeah, very good question. So the traffic light example, you could definitely use a time trigger model to count the remaining seconds for staying at certain state, or giving out a certain lights. That's a good case, good application to use time trigger model. For that case, you can also use event triggered. Well, let me see. Well, because I changed lab 1 a little bit before the start of the semester. In my first initial specification of lab 1, I actually, asked the students to use ultrasound sensor to detect the presence of the car. So in that case, a event triggered model is also possible. But for our case, time triggered model for the traffic light, looking at the time, and that's a practical design. But in terms of the implementation part, which I will talk more later, you could have different ways to implement this time triggered model. You can use timer interrupts. We have not talked about interrupts at this point, so you don't have to use it. You can use other functions, like you can count the elapse of time in your code and then track that away. But that's the implementation. But in terms of model, time triggered model is appropriate for this particular lab assignment. Does that make sense?
Yes.
Okay. Okay, default transitions. Default transition is enabled if no non-default transition is enabled, as no guard or guard evaluated to be true. So when is the above default transition enabled?
If neither of the guards are satisfied.
We actually have only one guard, right? This is for a different one.
Oh,
for the state coming back to state 0. So you're right. So if this guard is not true, which means that if the up is absent or down is present, this can be staying here. So that one was not shown because they don't produce. They are not. They don't have guard or produce output or go to other states. We will show default transition if they are guarded or produce outputs or go to another state. There's example here. We have a default transition. So if this condition is not true, we'll stay with this red state. but we're going to be outputting a signal R. Similar here, if this condition time G is not true, we're going to stay at this state green, but we're going to be outputting the signal G. So that's the case we will show the default transition. So this is the example that where the default transition doesn't have to be shown. It's similar to what we saw earlier, but it has only fewer transitions because those are kind of the default transitions. You can use this example to construct the formal mathematical model. That means we will use those 5 tuples to record the states, inputs, outputs, update function, which means you need to use a mathematical description to describe this transition from this graphical notation. Okay, we're going to look at additionally some definitions related to finite state machine. Stuttering transition. Stuttering transition refers to a default transition that is enabled when the inputs are absent, that does not change states, and that produce absent outputs. Receptiveness. For any input values, some transition is enabled. We use these default transitions to ensure that our finite state machines are receptive. So we will respond to any input values because we have this default transitions defined. Determinism. In every state, for all the input values, exactly one transition is enabled. So we have this many-to-one mapping. The reason I say many-to-one is it's possible that we take multiple input values, they go to the same next state, but you will not see a one-to-many mapping, which means that for the same input value, you will go to a different state or different states. That's the non-deterministic finite state machine we will see. So we have 3 kinds of transitions. We talk about the self loop, and we talk about the default transitions. And just earlier we talked about stutter transition. Let me go back a little bit. Just remind you, stuttering transition is the default transition that is enabled when inputs are absent, does not change state, and produce absent outputs. So let's see if you can answer any of these questions. Is a default transition always a self loop?
Yes.
Any different opinions?
I'm going to say no.
Why is that?
Because default transition is just when none of the other guards are really achieved. So I don't see a reason why you can't just have a default that brings you somewhere else.
That's correct. So a default transition is not always self-loop. It could be transitioning to another state. The second question, is a stuttering transition always a self-loop? Anyone want to try it?
I'll say yes.
That's right. That's by its definition that stuttering transition does not change state. So it must be a self loop. Third question, is a self loop always stuttering?
No,
Because
it could be stuttering only happens if there's all the inputs are absent, and a self loop could have an input
and output.
and output. Yeah.
Right. Thank you. Okay, so we're going to go into the next few slides about extended state machine. I hope you still remember the first few state machines that we talked about today, the garage, car counting machine, where we had m+1 states. Right. Here we're trying to do the same thing, but we are changing the finite state machine model with variables that may be read and written as part of the taking a transition between states. So let's look at the diagram on the right. We have just one state, and it's just counting. And the variables here is this C, which takes possible values from 0, 1, up to m. And the inputs are the same. We have up and down two pure signals, so they could be absent or present. The output is the output is the same as before the count, and that has possible values from this set 0, 1, up to m. And let's look at these transitions. The initial state is the counting. So on the first transition, we're going into the initial state, we initialize this counter to be 0, this variable C to be 0. And it is a self loop because it goes to itself. The guard is up and not down, and C less than m. So as you can tell that this is easy to understand. If there's a car going in and no car going out, so this is present, this is absent, and the garage is not full, we're going to take this transition. We're going to stay this same state, but because we have taken this transition, we're going to be doing a few actions. The first action is C+1. Okay. I'll explain later why it's C+1, not C. And also we have another action. This is the set action, which really means that we're going to be assigning a new value to the variable. And we have variable C, so we're going to be assigning the original value C+1 to this variable. Okay. And for the counting down is similar. Let's talk about this one. So in general, what you see, a extended state machine has fewer states with the help of more complex actions. In the standard state machines, we have this output action, but now we can have a set action which will update some of the variables, which you have to declare at the beginning. And you can have this initial set action associated with going into this initial state. And after that, the guard will be checked, the output action will be taken, and set action will be taken if the guard holds. And the reason we have to do C+1 in the previous case is that when when the guard is evaluated to be true, the output actions refer to a variable, we are using the values before the assignment of the set action. So the timing essentially is defined that when you take this action, when you take the transition, and all the values that you use to evaluate or use to calculate in the actions, those the values of those variables are the values before the set action, before the assignment of the new values. And that's why if you go back, look at here, we are going to output C plus 1 because at this point, C is still the original value. And then we assign this C plus 1 to variable C so that then when this action is taken in the next state, this variable C has the up-to-date counter of the cars. Okay, slightly more complex state machine. This is a traffic light controller, which keeps track of time and assuming it reacts at regular time interval. So this is a time-triggered model. And this is an extended state machine because we have a variable count, and variable can have value from 0, 1 up to 60. The input to the state machine is one pure signal pedestrian, and outputs are signal R, G, Y. So those are the control signals for the lights, and they're all pure signals, so absent or present. And as you can see that this state machine has 4 states, and initial state is red, and we have transitions. This is the guard, and we have the output action, set action when we go from red to green, and default transition, and we're going to stay here counting up. So as you can see, this count variable is a variable that we keep track of the time in terms of, I would say, seconds, assuming that the clock runs every 1 hertz, so you have to tick it every second. Okay. Now, this is how we define the state machine to control the lights. And of course, for the inputs, we should have something as a sensor to detect if there's a pedestrian present. And it's part of the design as the input to the system, and it could, change by the environment. So the pedestrian could, arriving any time, even between the clock ticks. So it may happen that you have a pedestrian arriving even before you, counting up the time or resetting the time. So there's uncertainty of this input signal in terms of time. We've talked about a lot so far about the state machines. These state machines are deterministic finite state machines. The number of states in these state machines could be huge. With the extended state machines, you not only have the information about which discrete state, the bubbles, the circles, the machine has, but also the next state depends on the values of these variables. So even though if you just count the number of states, you may think about, okay, you reduce the number of discrete states, but in terms of the transitions, you still have to consider the values of the variables. The numbers of possible states can therefore be quite large or even infinite. If, let's say, there are n discrete states, these bubbles, and m variables, each of which can have one of the p possible values, then the size of the state space is defined as this. So the number of states in the state machine, if you don't use a extended state machine to represent, that will be n times p to the square of m, to the power of m. So it's going to be a very huge number of states if p and m is large. In the next few slides, I want to introduce non-deterministic finite state machine. This is what we have kind of complementary to what we saw earlier, the pedestrian, traffic light control state machine. Here, this is the environment. It's the kind of how we capture the status of the environment in terms of how the pedestrian signal, pure signal, is generated. So in this case, what we have is input signals, pure signals are red signal, green signal, white signal. And the outputs from this state machine is the pedestrian, which is the pure signal. And the way we design this is we have 3 states: crossing, none, waiting. And we start with crossing. And if it is green signal, we will transition to none. Basically, we will determine that there's no pedestrian present. Essentially, the crossing is completed. And then from this none, we see there are 2 transitions possibly. This circle loop here, and then this transition to the waiting. And what's interesting or unique is that both of these 2 transitions, their guards are true. So their guards are true. And that means for this state none, when you transit to the next state, there are possibly 2 next states: itself or to the waiting. If it's transition to waiting, the output, the action will be output this pedestrian. And if you take this transition, the output will be nothing. Okay, there will be no output. And this pedestrian signal is what we need for the control signal, traffic light control signal that we saw in this diagram as the input. So the way these 2 state machine works are very subtle, tricky when it's in terms of how the pedestrian pure signal is generated. It has a lot to do with whether the pedestrian is present in between the time clocks, time ticks or not, and the environment itself could cause this pedestrian signals to delay. Let's say if the sensor has some unreliable issues or due to weather. So this kind of non-deterministic finite state machine will give us some flexibility to describe these unexpected conditions without worrying too much about exactly what the other light control system is at. Because the interactions between these two state machines are fairly complex. If you use also here a deterministic finite state machine to describe based on what you have in terms of control signals and the time counters, 20 seconds or 30 seconds, the number of states will explode. So it's better off to use this non-deterministic finite state machine to capture these fail-safe conditions and then make this transition next time. So I explained earlier that one of the reasons we want to use this non-deterministic finite state machines is to model these unknown aspects of the environment or system. If you run a robot and you expect that it goes forward, but if there's a bump, the robot may tip over or slightly divert from its original direction. So these are the environment that could affect the status or signals that you use as input. Also, for cases that you can use this non-determinism to hide details of the system. And there's more detailed explanation, example in the textbook. Another reason why a non-deterministic finite state machine is preferred over deterministic finite state machine is because of the size of the states. When we describe finite state machine, we can use graphical notations or mathematical notations. But its behavior here, where the finite state machine behavior is a sequence of steps. Really, what we can use this diagram. Well, the trace is a record of input states and outputs. So we start with the red state. If we have a green signal, and then the states change to green, and if we have a yellow signal, state change to yellow, and so on. So this is a possible trace of the finite state machine, and you can combine every possible trace together. You will see that it forms a computation tree that represents all the possible traces. This kind of representation is useful when you do formal analysis. Formal analysis is a method that can be used to validate your model, especially for critical applications. Before you put your design out to the field, you want to make sure that the design you have, the state machine you create, will not lead to any unsafe conditions, which could be catastrophic. We mentioned that the size of the finite state machines could be exponential if you use deterministic finite state machines. In general, non-deterministic finite state machines are more compact. If you took compiler or theory related to automata that shows a non-deterministic finite state machine can be equivalent to a deterministic, but with very small state numbers. in the worst case, a deterministic finite state machine may have exponential numbers of the states of the non-deterministic finite state machine. The sequence of the deterministic finite state machine and the non-deterministic finite state machine are very different. A deterministic system exhibits a single behavior because for given input, in the current state, you will definitely transition to one next state. And you follow this all the way further. But for non-deterministic finite state machine, you will possibly go to different states given the same input value. So that's what we see here. From here, you may go to these two different states, even when you have the same input value on the input signals. One more thing about non-deterministic, it's different from probabilistic or stochastic. In a probabilistic finite state machine, the transition has associated probability with which it's taken. So 50% of chance you go to state 1 and 50% of chance you go to state 2. That's for the probabilistic finite state machine. For a non-deterministic finite state machine, no such probability is known. So it's very random. Okay, so in terms of the finite state machine dynamic, discrete dynamics, we talk about models and read the state machines. And we talk about actors, input signal, output signal, their types, pure signal and numerical value types. We talk about a lot on the states, transitions and guards, actions. And we also talk about the determinism, receptiveness, and non-deterministic finite state machine.